right? So I'm going to call this our sum, and our carry is 0. If I do 0, 1, I get a 1 for the sum, and a 0 for the carry. Then if you do 1, 0, you get the 1 and 0 for the carry. And the last combination we can have is 1, 1, you get a 0, and a carry. Okay? So if I make this an A input, this B input, I can make a table. So then we have our carry and our sum. What do these look like? What is this one? What operation is this?
And
That's the end operation. This one is exclusive OR.
exclusive OR.
Yeah. So I can draw a circuit now for adding. So I'm going to have A and B go into exclusive OR gate. So this is my sum. And then I take these outputs and add them together, and I get my carry. Right? This is known as a half adder. You notice is, what if you have a carry from a previous, what if I started going, if I did 2 numbers, I have a 0 here, and then I want to add the next 2 numbers together. I can't use this circuit. There's no adding the carry from the previous circuit adder to do this. So we're going to create a full adder. And I'm going to start from the circuit. The book has this as well. I'm going to draw it a little different. So what we're going to do is we're going to have 2 half adders together. I'm going to first draw my other adder. We're going to change these up. This is now A and B coming to this first adder. And I'm going to OR these together. OR. So you're reading at the C out or carry out. Then we're going to have a C in, which is the carry in from previous addition. And then we're going to take exclusive OR of this result, and we're going to put it into the next adder. So in the truth table, I'm going to do some of them. We can see that how it works. A, B, and Cn. Then we're going to have my sum and C out. Basically, this is basically this addition. Think of it as the carry at top. When we do the first one, the carry is always 0. So if we have 0, 0, 0 here, exclusive OR is 0, still 0. Adding 2 zeros together is 0. We go across. Still exclusive ORing 2 zeros, so that's 0. We're going to add 2 zeros together so we get 0. We're going to OR 2 zeros together to get 0. So we get sum is 0 and the next carry is 0 on the circuit. We're going to go backwards. We're going to do B first in those zeros.
Why would it matter if you did A first or B first?
It doesn't matter. I just picked B. So, say we got 1 on B, 0, 0. So exclusive OR, 0 and 1 is 1. 1 added with 0 is 0. Go over here, exclusive OR is 0 with the 1, which is a 1. 1 added with 0, 0. 0 OR with 0 is 0. So then you can see is our sum is 1 and our carry was 0. So that's still correct. And I'm going to do one more. I do 2 more. I'm going to do both 1 ones. I'm going to do them all ones. Got 1, 1. So exclusive OR, 1, 1 together, 0. So exclusive OR, 2 zeros together is 0. 0 and with 0 is
1. 0,
0. So 1 added with 1 is 1. 1 ORed with 0 is 1. Alright. So we get the sum is 0, carry 1. So that's correct. And then the last one, we don't change much. This all stays the same. Except for we here, we have exclusive OR, 1 and 0. So this comes out to be 1. Then we add 1 and 0, which is 0. And we OR 1 plus 1, so we get 1 and 1. So that's the case for if we had all ones.
That's all ones with like a carry of 1?
Yeah. Just as they say, let's say if I was doing really addition, something like that, and then carry the 1 top.
One's coming from like another circuit?
Yeah.
Okay.
So,
That line is basically that 1 inch. That's from,
yeah. So basically, I can have, basically I'm going to take a bunch of these and put them together to make basically an 8-bit adder, a 9-bit, a 16-bit adder. Basically, the first digit, we're going to put 0 on the line. The first adder is going to use 0. So I'm going to draw boxes. Now we see the circuit looks inside. We sum it down into boxes. So that's probably something you'll see common. So I'm going to put a 0 on that line, and these can go to wherever we're getting our data from. And then this into another carry, and that goes into the end
Is
of the
that
other one.
C,
CN, sorry, it is what's the next one.
is that C out on the right?
Yeah.
Yeah.
Just like the same like that big circuit I had. So then, so you think of this as this is our next digit, our first digit, and then AV comes from another source, and then so I can put a bunch of these together and make it an adder, kind of bigger adder I need. So that's how computers add.
And those are like your chips,
Yeah.
basically, and then like the lines are your bus. Or
Yeah. So that's that one, yeah. These are all my wires going into different chips. Inside your processor in the ALU, these are just, you know, the gates are actually in there and they're just lined up like that, gates. So that is our full adder. So that's how the computer adds. One more type I'm going to go through. The book goes through a couple of them. I would read about them. There's a multiplexer and a encoder. There's the other two that they talk about. I'm going to do basically how a computer does memory, right? So memory, we call it a RS latch, which hopefully you can see is that's called a reset and set. So you add that. So I'm going to draw the circuit for this. This is my set line coming in, and I'm going to go through two NAND gates. And we're going to call this Q. And we're going to take that input and come down, and I'm going to add it to another NAND gate. And it's going to reset. Sorry. And yeah, I'll come back from that one, right? What you want to know is this circuit relies, basically is, when you change this, it relies upon what was previously stored on it, right? Because it has feedback back to itself. That's basically how it can store memory. Because it's feedback back to itself, it can store those bits into, a bit.
Is
So
it like a 1 on the reset? Does that remove everything in that storage? Or no?
let me go through the truth table for it. Kind of, probably one of the most confusing of all the circuits, because the feedback is, will throw you off. So if I have a 0, 0 on set and reset, and let's say I was previously had my Q and Q not 1, so I have 1 here, 1 here, and we have a 0 here, and a 0 here. Now I have to go through the circuit to do this first. So I'm going to go up here. So 1 NANDed with 0 is
0?
it's a NAND.
One.
1.
1
Okay.
is a 0?
Yeah,
Man.
it's a NAND.
Okay.
Yeah, this is a NAND. And so then it gets comes down here, 0, 1 and together, you get a 1, right? And then what happens is, go back up here, right down, yeah, 1.
Yeah, that's right.
And 1. Back up here, 1, 0. So yeah, so we keep going around like this until the thing gets stable. This one is constant, so that one stays correct. Now we're going to do reset. I'm going to start with this condition. Oh, you want to say this is not allowed. Or basically you want to say is you should never get that result. Because if you wanted to know is, probably say is this Q not? This is 1, that's 1. It's not allowed.
Those two can never be the same value.
Yeah.
The Q's can never be the same value.
Yeah. So now I'm going to start with Q is 1, now it's 0. Set is 1, reset is 1. So now I go through 1, NAND with 1 is 0.
1.
Q is 0. 0, NAND with 0 is 1. Through. Right. And we're stable. So if I put, let's say I move this to be 0 here. In the beginning. This comes over here, I get 1. Sorry, this will have to be 1. Can't have it that way. So 0 over 1 is 1. We'll go back to the top. 1 over 1 is 0.
1.
So it's stable. Okay?
There shouldn't be 1 at the top.
Yeah, it should be 1.
This is 1? Yeah.
But 0 NANDed with 1 is 1, right?
Mhm.
For your top circuit.
So it's switching.
Wait, 1 goes here. Oh, yeah, that's right.
So
This
that
is
takes
1,
you
so it
back.
goes through here. 1 over 9 is 0. This changes to 0. 0. So 0 now is 0, still 1. And so, like I said, is basically as we reset the circuit, it was 0, 1. Now it's 1, 0. Right?
What's the point of that?
What do you mean?
To have it just reset the loop like that?
Memory.
It's from memory. In a second, it'll make sense. There's something else we add to this. So, in this state is basically we say is we set the value to 1. Basically, we set Q to 1, and this one we set the Q to be 0. Right. Or maybe we want to say is it's clear. So basically, is we cleared the output on that one, and then if you put 1, 1 on the circuit, we'll put Q and Q naught here. Basically, is it's hold. So if I make both these 1, 1s, these don't change at all. Right? Okay, that's the first part of memory. But as you can see, it makes absolutely no sense in a way. We actually want to set data. We want to set and hold a 1. We want to set and hold a 0. So we need to create what is known as the latch. So gonna use the same setup here, but we're going to add basically our data. It's gonna go into the top there, and then we're gonna have an enable. Okay. Oh, okay. So we keep those, and we make data and enable. So if you want to think about it is, if enable is 0, memory shouldn't change, right? We shouldn't have to, we won't want any data to change. So if I'm currently in this state, let's say I want to set this memory into zeros, and put my E is 0. 0, NAND with 0 is 1. This goes down here, not 0, so that's 1. 0 here, so I have 0, NAND with 1 is 1. I go through here, we go here over here, so 1 NAND with 1 is 0, and 1 NAND with 0 is 1, so it never changed. So basically, whatever, I'm just going to put these marks on here.
I guess I don't really understand, like, when you're one ending with 1 and that's 0, in a truth table, true and true is 0. So I guess I don't understand.
So, okay.
That's true and true.
It's a and, not and. It's a not and.
Not.
Well, it's a
Yeah, so and, you got 0, 0, 0, 1, 1, 0, 1, 1.
Okay.
We got 0,
So
0.
it's a not and, that's
zero.
what I meant.
Yeah.
Wasn't C.
It makes more sense for me to think of not and not.
See, it's the opposite of an and.
Yeah. That's why I said everything is opposite of what you're thinking. So, basically this is going to be hold. So, nothing changed when E was set to 0. So then we can do the same thing when,
What do you mean by hold?
meaning that we didn't change the data. Even though I changed, even though if this is always 0, I can keep flipping this here. I can flip this to a 1. It won't change the circuit. I'm going to do this one here. So if I change this to 1, 0, so I put a 1 here instead. So we have 1 ANDed with 0 is 1.
Excuse me.
And then we not, so we got a 1, 1. We got a 0. 0 NAND with 0 is 1. Go up here, we got 1, NAND with 1 is 0. Go down here, 0 NAND with 0 is 1. Goes here. Okay.
So it changed.
It's not supposed to change. At least I'm wrong.
We're going to be tested on this, right?
Huh? No, you won't be tested on these ones. Basically, you just want to say what is memory as.
So if the circuit's disabled, it's not allowing anything to the circuit, or I don't know.
Yeah, that's what it's supposed to have. 0 and 1. And 1 here. That's why I said these ones are memory's confusing even before. my bad. I'm sorry. I see what I did wrong. Sorry. Data is knotted. And,
It's funny it works for zeros though.
so this is always 0, no matter what. So now, this one, I'll go through the whole thing again. So I'm going to start with the first one again. 0, 0, previously was 1, 0. So 0, 0, 1. We get a 1 here and a 0 here, so we get a 1. We get, no, 0 and not with that was 1. Down, 1, no, not it was 0. So we stay the same. Now I change you to 1. And this is now 1. Oh, sorry, not this. This is 1. Still 0. 0. 0 now is 0, still 1. And 1 was still 1. Stay the same. Right. Sorry. My bad. That one over there. Okay. Then jump to doing enable. Basically is now I'm going to set this memory, basically this output here to 0 on this one. So enables 1 and data is now 0. So 1 nano 0 is 1. So you have 1 here, 1 here, so 1 nano is, that is 0. 1 nano with 0 is 1. 1 nano with 1 is 0. Back down to here. 0, nano is 0, is still 1. And then now I'm stable, memory is stable. See how I kind of have to go back and forth until basically as I'm stable on this line. And so now you can see that now I switched, basically I switched the memory. So this one I'm going to say is,
So if I understand this correctly, you don't ever use, the Q naught value is just a check value. You don't ever use that?
Yeah.
The actual output is the Q value?
it's also nice if you just want to get the, not like the
To make
inverse
sure.
of it. Basically, the flip, the knot of it. So you might find, someone might find it useful in the circuit. So we have that condition. And so hopefully you see that. I'm going to go through it. 1, 1. I'm going to set it to set to 1. And this condition holds. So, and then, like I said, we can put blocks and blocks and blocks of these together. Basically, is all your data. If I was trying to save this number goes to this block. This bit goes to another block of memory. This bit goes to another block of memory. This one goes to another block of memory inside the computer. And then probably Friday I'll show you some memory blocks that have all these in there.
What do you do with the center column, the S, R, Q, and Q?
I can fill them in. So like
Is that filled in with something?
yeah. So that's set. This is the reset block. I just didn't fill them in.
Oh, I see.
I
Okay,
just didn't fill them in.
got it.
To me, it's more of like just trying to say it's basically is whatever D is and that's enabled, you're gonna set memory to that bit that you want to save.
So the purpose of the RS latch is to make sure that Q and Q naught are never the same.
Basically, the SR latch is basically the hold. You want to say it just basically allows us to hold the memory. Basically, it has that feedback, so it's constantly electricity is constantly flowing back and forth. And so basically, when you have the 1, 1 there, they call it a race condition. It's basically would constantly be flipping around. If I went through and I would just be constantly going like changing 0 1s, 1 to 0, 0 1, 0 1, and so your circuit would never be stable. And so then that's why we can't have it at that state in the beginning.
You can't have what?
The 1 1.
1 1.
We can't start
Oh, I
just
see.
Q and Q not as 1 1s.
Because it would be making it unstable.
Yeah, make it unstable. Even though it would run, it's just that if I put it on a scope, I would just constantly see this thing flipping back and forth.
Yeah.
And so that's not useful for us. So, okay. Any other questions on memory? And that, yeah.
So is that how it saves it? It just keeps sort of circling through?
Yeah. And then basically you gotta keep going through the thing. And once it's stable, basically it's saved. So basically then I can turn off the enable bit. I can turn that back to 0. And then basically that bit that I just saved will always be sticking out because we had the 0 on the enable, which doesn't change any of the on the memory.
So it's just always flowing back and forth?
Yeah.
So that one diagram represents one bit.
1 bit to save 1 bit, yeah.
And so you'd have 4 diagrams to represent 4 bits on it,
Yeah,
or
yeah,
8 to represent.
yeah, you have a lot of those. Like, you have to remember them, they're like, the transistor's like 4 nanometers big, maybe smaller, just throwing out a number. And they're minutely sized, you know, that's why you can have a, 2 gig stick of RAM that's like this big, you know, that has millions of address locations.
It's a program that probably runs through it and tells you
Is
about
it called
it.
latch?
I couldn't see like a memory company doing this by hand on a whiteboard, you know what I mean? Like,
Oh, no, they have
you know, a trillion-
They have CAD programs that,
No way you could do that.
so, yeah.
But I guess you understand.
In the beginning we do it that way. And so, in the beginning we only had probably, 10K or something like that, where we can draw that almost on a board. So, I don't want to jump ahead. There's also other memory that you have in your computer that basically are just those by themselves. Okay, I'm going to go into probably one of the hardest things in this class. When we were doing Boolean algebra, probably some of you probably thought it was really hard and trying to remember all those rules. We're going to do the easy way. I'm going to show the easy way how to do that. Even though I've said it's probably the hardest thing for students. But it makes Boolean algebra easy. So this is what we call cardinal maps. I'm just going to abbreviate it to say K-maps. Right? So I'm going to first start with a truth table. So I'm going to have A, B, C is my input of this function. So those are my inputs, and basically this is my, that's my output, and I'm just going to put some random output here. I have no clue what is in the circuit. Basically, I have a box. A, B, C, and I'm getting some output V. Okay. And so that's what my output looks like.
That's an award.
What?
Those are awards.
Maybe. I'm not sure.
Oh,
Wait,
It's,
do they line up?
so you just guess those, you right?
basically, is I have a box. I have a black box. I have some 3 inputs going into this box, and I have some output coming out. And basically, I put a 0, 0 on 1, and I got a 0. I put a 1, 1, 1 out, and I got a 1. It's not OR together because these two would be a a 1, so it's ORed, and this would be a 1, they're ORed.
Is that like, but you use the V at the top of it?
Yeah, basically V's is,
Oh,
I'm just
yeah,
calling
I guess I
it
was
V.
just, V's in order, so I just.
Yeah, no,
wondered
sorry.
if
V's, it's just a name I gave it, like
Is that
A,
like
B, C,
value or something?
Y, you know what I mean?
Okay, because V's would be a little problematic in truth tables if you're using it to represent. No, it's because it's an OR, so.
I do Y, is that better for you?
Yeah, there you go. Sorry, just saying, speed math.
Okay, so that's an output Y. Basically is, I want to know what's inside here. I want to know what transistors and gates are in that box. And so this is the K-map. Okay. So I'm going to create a graph or a table. And so basically the top part is my A and the bottom is BC. So if I want to say it, down here is going to be a truth table and over here is going to be a truth table. So two options for A are 0, 1. And then for BC we have 0, 0, 0, 1. I'm going to show you for a loop here. I'm going to put 1, 1 here and then I'm going to put 1, 0 here.
You would.
Yeah. Okay. I'll explain why I did this one. Basically is, in a K-map, we only want the variables to switch one time. Does that make sense? So if I went from 0, 0, I only want 1 bit to change in this number here. So that one changed. I go to this location, I only change this 0 to 1, that stayed the same. And then the same over here is this stayed 1, this went to 0, so only 1 bit changed. That's what I want to make sure I keep it from 1 bit. You want to say here is 1 bit changed to 1, and then it loops around again. Same with down here. It loops up and around. So I changed this bit here to 0. So that's what we want. We want it to do. So then, now you can say, so this cell here is 0, 0, 0. So A is 0, B is 0, C is 0. So inside here, we have 0. Right?
Do that again, I missed.
So A is 0, B is 0, C is 0.
Oh, I see, you're doing
So
the
this
first
is-
line. Okay,
Yeah,
got
I
it.
got to split these up. Yeah. That's better. Then I'm just going to label these. So M0, M1, M2, M3, M4, M5, M6, M7. So we can see this is M0, M1, M2. Why is M2? 0, 1, 0. So 0, 1, 0 is M2. So M2 is down here. And then this is M3. And then M4, M5, M6. Yeah. Alright, so then now I can fill in a little faster so I can go.
What is that? I can't.
These are just M's.
That-
These are just matching, basically, these are the columns. I just labeled each of the row columns as M0, so then I can just quickly just follow this.
You're just matching patterns is what you're doing.
Yeah.
right?
So like, M7 is, A is 1, B is 1, C is 1. So as I said, M7 is here, so 1, 1, 1, so M7 has a 1 in it.
So is that an M or an N?
M, these are all M's.
As in
As in Nancy?
Mike.
Mike, yeah, M. It doesn't matter, I can call them N's, I can call them Q's, it's just
Yeah,
a
it's just
name
a
I gave
variable.
them. Yeah.
Malnutrition.
So we got 0, 1, 0, 1, 1. So I filled in my blocks on my Cardinal map here. Switch. Right. First I'm going to do SOP, which hopefully you remember is sum of products, and basically is ones. So I want to know where all my ones are, and so basically I'm going to group ones together. They can be one by itself, 2 ones together, 4 ones together, 8 ones together. So we want to think of it as the same as 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 8. So we do the same kind of logic when I'm going to do something in a second. So I can group groups of 2s, groups of 1s, groups of 4, groups of 8s. So I'm going to draw these circles of groupings. So this is a group of 1s, that's a group of 1s, and that's a group of 1s. Okay. These groupings are known as input kits.
Does the book talk about this?
No,
It doesn't?
there is 2 notes. I have 2 notes in the notes directory, and then there's a little .exe program that will basically you fill in 1s and 0s, and then it will give you output. Yeah.
On that it's 0, 1, 0, and over here you have 0, 1, 0, 1. Like 0, you have, on one you have it, the answer is 0 if it's 0, 1, 0, and the other one you have 0, 1, 0 is equal 1. If they don't match up.
Which ones will match up?
What numbers?
M2?
M2 is 0. M2 is 0.
Oh.
And 3 is 1. So since the 0, 1, 1, so yeah, A is 0, B is
No,
1.
I was looking at the one higher than that.
Oh, this one? Over here?
Yeah.
So M5 is 1. M6 is 1. But, good.
No, but that's okay.
Continue.
Okay. Alright. So, you want to look at it as,
So is that going down M0, M1, then M3, then M2?
yeah,
Now we're trying to read it.
yeah.
Is there any real reason except for you only want only one of the bits to change?
Yeah. We only have
Why?
1 bit to change.
Is there a reason why we want that?
If I can finish, I hope you'll see why.
Okay. I hope I see why.
I just quit.
I'm sorry about not writing clear. I'm trying to get through this as
Some
fast.
of us have eye problems.
That's 6.
Okay. So then I'm going to create groupings. So if you want to think of it as if A does not change in this grouping here, so I'm going to do this circle here. So A does not change, and B and C are constant. They're both 1s, right? So I can
What do you mean
say,
by A does not change?
but basically we don't care. I say we don't care about A. Make sense? No matter what A is, it could be 0, 1. B and C are there, but always have to be 1 for my input to be 1s, right? Make sense?
No.
So I don't care what A is, because B and C have to be 1s to get 1, 1 in this input. Basically, is to get 0, 1, 1. I don't care what A is because A could be either a 0 or 1, but A, B, and C have to both be 1s so I can get basically 1s on the output.
I have a
Okay.
question, Ryan.
Makes sense.
You're throwing A, B, and C through that black box, and you're
Yeah.
outputting these things. You're trying to analyze what's inside the black box.
Yeah. Yeah. And so I'm going to create this grouping here, would be known basically as B and with C, right? B, ANDed with C is 1. B ANDed with C is 1. Alright?
Okay.
So that's what we call this grouping as BC. So that's why we can get 1s on this end. Think about it is if I have B is 0, I'm ANDing with C, it's always going to be 0. So basically is I could get this result right now. And then no matter what A is, so they say like if I want A is 0, I don't care what it is. I want to be that. So that's the first grouping. So the second grouping is, I'm going to do this one here. 1 is the same. And we see that C is the same, but B can be either 1 or 0. So we don't care about B, we only care about A and C. So the next one is AC. Okay. And then the last one, we
So
see
we're
that.
doing an and on these.
Yeah, we're doing and on these ones, yeah. That's why I said the sum of products. So basically, you see these as sums, well, not sums, but products of each other. So the next one is going to be AB. Okay. Now I can go BC or AC or AB. This is why. So we do this on hand. Just think of it as so. I'm going to do A, B, C. So 0, 0, 1. We have 0, 1, 0, 1, 0, 0. So or those together we get 1. Things AND together we get 0. Those AND together we get 0. Those AND together is 0. Or all 0 together we get 0, which is what we got on this one. Right? I'm going to do the one with the 1. So let's do A is 1 and B is 0, C is 1. So now we know this is 0, 1 plus 1, 1 plus 1, 0. So this is a 0 ORed with 1, ORed with 0, 1, which is what we got on 5. So now I know what's inside this box. Basically is I can draw what's inside the circle, or inside this box.
So you threw a few test cases through it to find out that you're on the right track, is that
Yeah.
what you're doing?
So now we can say is so we gotta have AB goes through an AND gate, A and C goes through an AND gate, and B and C goes through an AND gate, and then we OR those together. Awesome. Get Y. Right. Now I know.
For the A, B, C, and Y, the first table you created, was that just a bunch of random numbers you threw in?
Like this one here?
Yeah.
Yeah.
Or did you like kind of logically select those to get this?
No, I just ran it this way. And so think of it as I got this input and I want these results to be on my output. What circuit do I need to design? And so basically I can design a circuit on what I need to have on it.
What if you can't find a pair of ones?
What do you mean? Pair of ones? Like I said, you can circle 1, 1. You can circle 2s. You can circle 4s.